We're ready.
Thank goodness for that. Okay, so this is the final review session. And now that we have an audience of 2 plus videographer. So here.
Oh yes, and one more thing, students. Don't forget about the donation program. If you're interested, just contact Dr. Lambers, and he'll be the middleman for donations if anyone wants to. You can be a grand benefactor for just $1,000. Most places do $5,000 or more, so it's a steal.
Well, at least I'm not the one who's having to make a donation this time. Based on what I've done so far, I'm already a plus benefactor just based on the DVDs.
Oh yes, that's like a free McDonald's meal, I think, or something that comes with that. I don't know, I haven't made that up yet.
Well, too bad I was just there. So here I have the final exam.
Let's get closer to that.
No, I haven't pages turned. All 21 pages. So for 20 regular problems plus 1 bonus. So the coverage will be 6 problems on chapter 11, which is on differentiation. 6 on chapter 12, and 8 on chapter 13. So real quick, I'm going to indicate what types of problems are, and then we're going to go through some. We'll see how long it takes. So we have tangent plane and mobile line. So given a function at a point, write down the equation of a tangent plane at that point and a normal line. There was a problem like this on the first take-home exam. Linearization, come up with a linearization of a function at a point, and use that to estimate value of a function at a nearby point just by using a linearization. There's the chain rule. For compositions of functions of several variables. There's also directional derivative. So give a directional derivative at a particular point for a given direction. Find the local max-min and saddle points. And finally, the method of Lagrange multipliers. Okay. Now I'm going to star a couple of these. Any topics that I put a star next to are ones that also will appear on the oral exam for anyone who chooses that route. Okay. All right. Okay, so that's the stuff from chapter 12. Versus chapter 11 rather. So for chapter 12 we have iterated integrals. So if I just give you a double, triple integral, where an iterated integral, it's already set up. So you're just going to do the integration on it. Let's see. Just general double or triple integrals. Over a given region, where you're just given a description of a region, and from that you need to come up with the limits. So, in keeping with that, you may need to switch to polar coordinates if it's a double integral. or spherical or cylindrical coordinates if it's a triple integral. So depending on the integrand you have, a type of region you have, if a region is kind of cylinder-like, you should use cylindrical coordinates. So there'll be more than one problem that'll be of this type. Okay, quite a few actually. And then change of variables. So if you're given a transformation, we have to compute a Jacobian and put that into the integrand. This is something that can also be a topic for the oral. All right. So that's chapter 12. Chapter 13. 8 problems from here. Line integrals. And I want to point out there's 2 types. Line integral of a scalar function, line integral of a vector field. You have to keep that in mind because the formulas are different. So for a scalar function, you're integrating the scalar valued function f where x, y, and z are parameterized by t. Yes?
I forgot, which book is this in, or was this announced?
Oh, the chapters?
Yeah.
These are for chapters in Stewart.
Okay.
Yeah. And then you have to fill in this expression, magnitude of the tangent vector. So that's when it's a scalar valued function, because this is a generalization of the arc-leg formula from last semester where f is equal to 1. But the ones we've dealt with more often, the more important ones really, are vector field. So you have a vector field capital F evaluated at x of t, y of t, z of t. And this vector, if you take the dot product with the tangent vector. So normally this one actually tends to be the easier one to integrate because you're not dealing with a stupid square root. Okay, but you can expect problems of both kinds to pop up on so you give it a description of a curve. Okay. Let's see. We also have fundamental theorem. Of line integrals. It says that the line integral of a vector field that is a gradient. So if big F is conservative, it's a gradient of some little f. And in that case, a line integral becomes particularly easy. You just evaluate f at the endpoints of the curve. And if the curve is closed, therefore beginning and endpoints will be the same, of course, then the integral will turn out to be 0. We have Green's theorem. So if you're given an integral over a curve, 2-dimensional vector field, then you compute these derivatives of p and q. Chances are, like what happened on the third exam, you get something simpler to integrate, even though you're going to have to do a double integral over the interior. Divergence and curl. This is like number 6 on the third exam where he had to prove an identity.